The LIGO in India has proved Einstein wrong.
I just wanted to find out what is going on with this reality. Is this the truth, or are we, in some sense, being lied to? You can't change space, you can't change time. That's false.
Where do we start? What's a good way to at least catalyze the ecosystem? Why it has been so important for scientists around the world?
It's not just a mathematical curiosity. I think black holes are essentially the engine by which everything in the universe is created. If you give me just 10 top-tier kids from any of these high schools or universities for 5 years, I'm sure I can make some huge, front-page news discovery.
So, okay, you're not joking then. This India detector can actually... Rana, welcome to SparX. I think I heard you just say you're an excellent science communicator. So I think
I'm best in the world.
Best in the world. Okay.
That's right.
Well, you have to now live up to that claim. Well, you have been in many ways living up to the claim through your science, Rana. I think gravitational waves have been literally making waves around the world since 2015. Let's start there. First of all, what are gravitational waves? Why are they important? Why so much excitement and so much coverage about gravitational waves?
I mean, as people say, gravitational waves are the ripples in space and time. And I think that's already, that sentence sounds like it's simple, but that's such a complicated thing to get your head around.
Yeah, it sounds like a fancy, sentence that scientists made up to make science look cool.
I think
what are ripples in space-time?
Exactly. If it was pre-1990, it would be very difficult to understand this. But because of the movie The Matrix, now it's easy to explain it. It's as if you're living in a video game.
Yeah.
You're a three-dimensional character, and then the coordinates in the video game are being warped while you're moving around. And so it's where you live. You feel like you're living in a 3D space-time, but that thing itself is being warped. And it's as if you're in a 2D surface moving around, and that thing starts waving. So it's like ripples in a pond, but it's three-dimensional ripples in a pond. And it's the most mind-bending thing. Because for us as human beings, space is what it is. You can't change space. You can't change time.
Yeah.
But that's false. Space and time are always being changed by the gravity around us.
But still, help understand ripples. I can very easily visualize ripples in a pond. You throw a stone and, you can see this thing oscillating, going up and down. I don't see space-time ripple, maybe in the movie Matrix, but what does it mean like real world,
Yeah, in the real world, because we're far away from any serious gravitational source, for us space feels very flat. But there's a thing about time bending that really, really is true. That if you have a clock here on the Earth and you have one in space, the one on the Earth will just run slower. And that's because time on the Earth runs slower than it does on the moon, for example. So if you had a brother on the, your twin is on the moon or something like that, and you lived for 1 million years, your twin would look older than you by the end of it. But the ripples in space-time are much wilder than that. That's your ripple, your ripple on a pond idea is exactly right. So you drop a rock into the pond and you see a wave emanating from that. And what we see is when black holes smash together, that's exactly what it is. It's like you've dropped a rock into the pond. Except now when you look at those ripples as a human being, if you look into the night sky or something like that, it would look as if the stars are actually moving around. So it's a wave in the movement of light. It's a stretching of physical objects. It's the very nature of reality is moving back and forth. And that, when you visualize that, I live with that in my mind all the time. And so I have a different experience in life, I think, because this whole thing in front of us feels a little bit artificial.
Okay, I'll come back to black hole and we'll really, try to, for once and all, explain, why they're so interesting. Yeah. But before that, so there's these ripples in space-time that I guess people call them gravitational waves, and this is something that's been your day job for last 20 plus years.
Yeah.
Why it has been, or longer, why it has been so important for scientists, around the world, and you've been kind of in the thick of this for a while to be able to measure. And from what I understand, it's also probably extremely complicated thing to do, from engineering perspective. So why, it's been so much interest in this?
I didn't know it would be so hard when I got involved, and maybe I wouldn't have gotten involved if I knew it would be so difficult, but I got involved because...
Is that true? Look, even entrepreneurship, everyone says if I knew it was so hard, I will not get into, but people get into like extremely hard thing. Do you really believe if You'll probably still get it. I think that's what drives somebody like you or many other people who do difficult things, because you get into it because it's so hard.
Once I was in the middle of it, yes. But there's several times I was thinking about quitting because the future looked bleak. And, I thought, how can I go on? Maybe I've just made the wrong choice and it's never going to pan out. But if, I started in 1997, and if you had told me it'll be almost 20 years before this pans out, as a starting student, if you said 20 years before any success, I don't know if I would have had the heart to do it. But I'm not an astronomer, or I've sort of become an astronomer along the way. But to me, the main thing was, I just don't believe it. I don't believe this theory of relativity. I don't believe there are black holes. I don't believe in all of this stuff.
This was when you were starting your journey as a profession.
Yeah.
Scientist.
I just thought it must be nuts. This Einstein guy, what he's saying, just what you were saying, I don't see it in my daily life. Yeah. I mean, I was driving, I was an auto mechanic at that time.
That's quite a statement to say, like Einstein might be nuts. That's...
Yeah.
You're not saying it or allowed to anyone because they won't otherwise.
No, I did.
You did?
Yeah, I did. That was my first physics professor.
Yeah.
I said, listen, I have a motorcycle and I've driven at 150 miles per hour on the freeway. I've never seen any time dilation or any of this stuff. Look around. This seems like mathematical.
150 miles per hour.
Yeah.
You were quite nuts, I guess.
Well, I was a teenager, so you can do those things.
All right.
So it's, but even at that speed, there's nothing going on.
Right.
And, this thing that you have to be almost at the speed of light to see this effect.
Yeah.
It didn't really, sink into my mind at that time. But I got into college with that feeling that, how hard can this be? In a few years, I'm sure I can prove this Einstein guy wrong. I'll just make a few measurements and it'll be direct proof.
Yeah.
And then
How did it go for you? I'm still trying to prove him wrong, or you have managed to prove him right through most of your work?
I would say so far I haven't found any mistakes. But that's, I'm only halfway through now.
But let's also talk about, this, you and your group, been extremely successful in these gravitational waves were almost like, more fictional things, in 90s and 2000, but not anymore. So just to help explain, what have we managed to do?
Yeah, it's just as you say, nobody sees these ripples, when you're just in your daily life. Even if somebody comes by at 150 miles per hour, there's no gravitational waves from that or anything. And so it's extremely hard to measure these things. And the reason for that is basically the space-time that we live in, which you should imagine as a kind of fluid. That space-time itself is incredibly stiff. So it's a fluid like as glass is a fluid or something. It's a really stiff fluid.
And this is all pervasive throughout. We should visualize in the entire visible universe.
You can visualize the entire universe and imagine there are grid lines that are giving you the three-dimensional coordinates to that. And so now something happens out in space and you would see the grid of space and time actually changing. So the rate of time flowing and the distance between objects would change. But anyway, you need a lot of oomph in order to make space bend because it's so stiff. And so you need the most powerful events in the universe. And those things are happening far away from us, sort of millions and millions of light years away. And by the time the vibrations get to us, they're so imperceptibly weak that even Einstein himself said, I mean, come on, look at these numbers. Like, who's ever going to measure this thing? Let's just stop talking about this. And people just ridiculed the whole idea that, first of all, the numbers are astronomically tiny. It's like, after the decimal point, there's something like 20 zeros before there's a 1. So usually in physics, if you get a result like that, you just say, let's just call it 0 and let's be done with it. But, you had, I would say, some nutty people in the 1950s and 60s who said, I think I can do it. I put it together and I'm so clever at this experimental skills. I'm really going to measure this thing.
They must have in their 20s and to be able to be
That's right. Yeah, they were nuts and they were also wrong because they had miscalculated by 10 orders of magnitude or something, like what's the level of the signal. But I think it was, because of that optimism that I can do it, everyone says I can't do it and I can do it. Like you have to have that kind of spirit that I'm going to prove these people wrong.
Yeah.
Like I foolishly thought I would prove Einstein wrong, something like that. But the field got started by this fellow, Joe Weber. And he immediately thought he had detected something. It turned out not to be quite right, but because of the enthusiasm, this whole field got started. And So we are trying to measure things on the Earth, which are, it's hard to even explain this or visualize this thing, but here we are roughly the size of a meter or something, and an atom is 10 billion times smaller than we are. And what we are measuring is yet another 10 billion times smaller than an atom. So as we are to an atom, the gravitational wave is to the atom.
Wow.
Something like that. So it's a...
yeah, and this is like, maybe I'm going to rephrase from one of your talks that I watched recently is, this repulsive space-time is basically, expanding and contracting space around us. If we are able to somehow get an extremely powerful gravitational wave, which is not going to happen, but just, then we literally shrink and expand while the wave is passing through us. And I guess that's what's happening with these distant events. And I think you mentioned in your talk that these waves are so faint that, the entire Earth in some ways get expand and contracts, but by not more than the width of a human hair, or not even that. And you are trying to measure that change as these waves hit us.
Yeah. It's, no, it's even less than that. The Earth is about 10,000 kilometers in size. And so these things will change the whole Earth by less than the size of one atom.
And you are able to measure that?
Routinely and with no problem anymore. And that's the thing that amazes me. I was sort of in the middle of it where it was feeling like it was possible.
Yeah.
And we got it started. And now what the team has done is they're just detecting these things all the time. In fact, people sometimes keep on checking their email as a black hole merger happens. It's become that normal for them.
I think it's worth repeating. You're saying that when these gravitational waves hit us, the entire Earth moves by basically about the width of an atom, which is, extremely tiny.
Yeah.
But your instruments are able to just routinely pick it up without missing. We'll maybe get to, some precision engineering of that, which must have been, I'm sure a lot of things got invented along the way. Otherwise, something like this is definitely not possible. But maybe let's take it, zoom out to, through these gravitational waves, we are trying to understand something about the universe.
Yeah.
And a lot of them, from what I understand, mostly is extremely massive objects colliding. But they're so far away, billions of light years away and so on. Why do we care?
No. People care for different reasons. I would say there's a menu of reasons why you should care. I mean, as you said, there's a lot of engineering challenges. So that's the practical point is you have all these people who are, for whatever reason, they're obsessed about black holes.
Yeah.
And because they really want to know about it, they've done all of this engineering development, which is now of use to the rest of the world. For myself, as I said, I'm not an astronomer, but I just wanted to find out what is going on with this reality. Is this, when we look around with our eyes and our ears, is this the truth, or are we in some sense being lied to? That there's a deeper reality on which we live. And for everything, it's a kind of maybe reductionism or something, but you say, what is a proton? And what's inside the proton? Or what's an electron? What's a black hole? What is really space? Is it just a word that we use, or is there some deeper microscopic meaning for what space really means, or what is time? Those kind of foundational questions. And the reason the black hole is so important for it, that's the place where our current science breaks down. We're not able to really describe to you, why black holes seem so mysterious. Is because every feature of the black hole, whenever we describe it, if you're out on the streets and talking like this, people will just put you in a mental hospital because they think you just don't know what's happening. You're just so deluded. But everything around the black hole feels like that. And out at Caltech, we're sitting around and it's a normal lunch conversation about black holes. I've found this, I think this is happening. But when I zoom out and I think about the conversation, it sounds like a sci-fi adventure that you're on.
Well, it sounds like, more than that, I think, you can also make a blockbuster movie out of black holes, which I think you and your colleagues did, I think, from what I understand, many of you are involved in Interstellar, which kind of treated black hole as if it is a fairly well-known entity. I think your colleague Kip Thorne here wrote a book also, Science of Interstellar.
That's right.
But how do we manage to do that, if, as you say, black holes are mostly unknown, there's a mystery that we don't know what's inside, but yet we made it, movie which made it sound like, something we can almost navigate.
Yeah, I think that's the amazing thing about it, is it started off as a kind of mathematical curiosity that pops out of some equations. And it's an amazing thing about the universe that this mathematics from the 1930s or something turned into something that we can observe in the universe. And that unambiguously, there are black holes out there. I mean, you can observe them at the center of the galaxy, which is not too, maybe 50,000 light years from where we are. And you can observe them almost to the edge of the universe.
Yeah.
And it's not just a mathematical curiosity. I think black holes are essentially the engine by which everything in the universe is created. Like galaxies have formed because of black holes, and they're such a major player in the story of the universe. It's not just, for me, I want to find out what is the true nature of reality. But if you care about why does the universe look the way it does? Why does it have spots instead of no spots? That's because of black holes. And now what we're learning, it's like, if you have your eyes closed and you walk into an empty cave and you hear this sort of squeaking of bats.
Yeah.
Okay, that's unpleasant already, but that sound of the bats allows you to know like what's the shape of the cave, how deep it is, and that kind of thing. And now the detection of black holes is so numerous. You can imagine it like this. We're in this empty universe.
Yeah.
We've always been just looking around at the bright spots, the stars.
Yeah.
But now if you close your eyes and you listen, you can find out the shape of the universe in a different way. And it's like being in a dark cave. But we're finally turning on our ears. And the universe is incredibly, it's like being in the jungle or something. The kind of things that are going on. If you had told me this stuff 20 years ago, that this is how it is, I would have said, there's no way. There's no way. I can't even imagine how I would make the universe like this, with this many black holes of this size. What is the story behind this? It's kind of a mystery.
So let's try to unravel the mystery to the extent we can. I understand, fundamental black hole continues to be huge mystery, and that's the allure of or almost like deep need to want to understand. But how prevalent are these? So in our own galaxy, are there hundreds of black holes, hundreds of thousands, millions? What's the order of magnitude?
No, I think you're now finding my lack of astronomy education or something like that. I don't know the number. I shouldn't say the number.
Okay. I should ask Shri. I think when he was on this podcast.
I think he would. Yeah, he would know. Any astronomer worth their salt will be able to tell you what's the size.
Yeah. I think my kids make fun of me because whenever I start discussing science, sooner or later I start asking how much questions, and how many atoms in in air, whatever, how long does it take a photon to escape sun and so on. So maybe that's my way to engage with science, but let's come back to
I think they're great questions. How many black holes? I would say it's like this. In the galaxy, there's about 10 to the 13 black holes or something. So trillions of stars in the galaxy. Half of them are in pairs. They're binaries orbiting around each other. And for things where the stars are something like 10 or 20 times heavier than our sun, or even more, eventually they'll collapse into black holes.
Yeah.
Because they'll run out of fuel or something and they'll shrink like this. They'll go through all kinds of essentially like caterpillar, butterfly stages of collapsing and exploding and so on. But finally, there's nothing you can do. The inescapable truth is that if you're heavy enough, you'll collapse into you'll become a black hole. And so these things are now orbiting each other all over the galaxy, that's fine. It goes on. But if you calculate what that means, essentially for millions of years, they would keep orbiting. So then you would never find anything because they're just slowly dancing around each other. They're not actually collapsing.
Yeah.
And the big surprise of my life has been, that's not quite true. They don't just keep on doing this kind of thing, but there's a huge number of them, for whatever reason, that are being forced into this dance of destruction or something like that, where they do this and then they're collapsing at a huge rate. And so the whole life cycle of stars and what happens to them, that story is now rewritten, I think.
Right. And with the whole LIGO setup, as you're saying, you are able to routinely measure. You think you're getting large percentage of these black hole mergers, or still what we are observing? And also, again, what's the magnitude? How many such events you detect each year? Which of them become interesting events versus not?
I think now it's, I hope I'm not revealing something I shouldn't, but I think now it's something like 2 or 3 per week that we detect. And when I first started, we had hopes that, maybe in 3 years we'll find one that will be just sort of marginal.
Yeah.
And it's this technical work that the team has been doing that's turned it into this amazing new instrument.
Right. So let me try to visualize, and maybe you can take us inside LIGO, right? So you have these, I think, 3 or 4 kilometer long arms and so on, and then probably have some of the students mostly working on this, and twice or 3 times a week something beeps in this instrument,
Yeah.
and then you are able to see that in a
Yeah.
galaxy far, far away,
Yeah.
this
Yeah.
neutron star and black hole merge, and this happens. This is
That's
everyday
it.
physics now.
Yeah. Yeah. I would. It sounds a little complicated with this like lasers and tubes and
Yeah.
what's going on, but I think an easy way to visualize it, if you're, like when you're in the shower and you're singing, it sounds sort of pleasant because the
Not
shower.
for everyone, but not for me at
Yeah,
least.
I find
I don't want to hear myself sing. In
I'm
the
a
shower.
better singer in the shower than I am outdoors.
You're already a great communicator, a great singer. We'll find out by the time we are done.
Well,
We're
only
already
in
great.
my own universe, I'm
Right.
great. So that's a different thing. I think that's because you hear the wave, you're singing, and it bounces off the wall of the shower, and you get it back, and so you can sort of tune up your voice. So it's like a auto tune or something that you have. It keeps you tuned up, but what that relies on is that the sound wave goes to the wall and then comes back in a finite amount of time. Yeah. And essentially, that's how the LIGO detection works. You send a laser beam this way, and you send another one this way, and you wait for them to come back. And most of the time, because the two lengths are 4 kilometers each, it takes the same amount of time to go this way and that way.
Yeah.
And you can imagine it if you're singing, you can sort of make a clapping noise and hear the echo coming back, and you can hear it coming from some other side. And that will tell you about, where's the wall in this direction, where's the wall in that direction. And if that changes, somebody has moved the wall, or there's an object has moved in the way, and that differential measurement, because you're taking differences, it means that you're not sensitive to your own whatever is going on. What are you exactly singing? You're just measuring the difference of something that started out the same. And so that allows you to do really sensitive measurements.
Right.
So that's essentially the LIGO. You send the light pulse in the two different directions, and when they come back together, either they're interfering in the way that's destructive or constructive. So they add up or they subtract. And that difference is all that it takes.
And you have kind of 2 copies of these instruments in the US, and I'm assuming most of these events you kind of measure in both. If you don't, then probably it
That's
might be a
exactly
suspect, right?
Yeah.
And you've been involved in trying to build something similar in India. How's that coming along?
Yeah. We've always needed one because when things happen in the universe, you'd like to know where they are. And if you have just 2 LIGOs, you cannot triangulate with 2 things because of the and triangulation, you need the third. And you could put it in any other country, I guess, but I thought India is just sort of the ideal place for this. There's a culture of innovation. There's a strong history of mathematics and science. And so that it's a country that has the actual capability to do this kind of thing. And then the scientific impact is, of course, I'm still trying to prove Einstein wrong. So I'm always looking out for what's the next way to do it. And people here wouldn't like me to say maybe that we're going to prove Einstein wrong, but if there's a problem in those equations, this new Indian detector is the one that will find it.
Yeah, I think our podcast team will love this. I think they're going to title this episode as Rana wants to prove Einstein wrong, and they'll get all the views they want for this. But
I have nothing against Einstein.
But he continues to be so relevant. I had a talk with David Gross also a few weeks ago here, and we talked about both him being inspired as a kid by a autographed book of Einstein he got. But this is something, he's a larger than life figure. It's impossible to have a science oriented conversation, at least in public. I don't know how it is in private, without Einstein showing up. Looks like his stock continues to grow and grow. The more people want to prove him wrong, the more his stature just keeps growing.
Yeah. I think it's because, special relativity, I think you could argue everyone, like 4 or 5 other people had those equations in their notebooks and they could have done it. But I think a lot of them just thought, this is a curious thing or something like that. But I think he had, the power to come out and say, no, this is not just math. This is how it actually is. And then the bigger step, I think, that's fine. There was a lot of evidence actually for that kind of thing. I mean, no matter what Einstein says publicly, privately, he knew that the experimentalists had already ruled out the ether theory and those things. So that's fine. I give him, maybe not A plus, but I give him an A for that. But I give him an A plus for the next theory about how space and time works, because there was really no evidence for any of those things. And he just came out and said, if I just take these simple assumptions about what's true and what's not true, this is what the mathematics tell me what's been happening. And then over the next century, each time someone went to measure it, it was there.
Yeah.
And it's just such a puzzling theory, I think. And it was almost a one-person show to make that happen.
So if, let's say, hypothetically, if some future development of science ends up proving him wrong, what would that might look like? You think it's general relativity getting modified is the way that will happen?
Yeah, so that's my hope for this new detector in India. So this is a little bit technical thing, but it has to do with polarization. The two detectors, how do I explain polarization? I guess if you buy polarized sunglasses or something like that and you're driving around, all of a sudden you see different things. You see the sky is polarized. If you look and tilt your head with polarized sunglasses, the blueness of the sky changes. Or if you're driving a car, you'll notice that the windshield has a cross pattern in it. And that has to do with the fact that the stress in the glass changes the polarization of the light. So when the light comes at you, is the electric field waving up and down, or is it waving side to side? And that's rotated by passing through materials and that kind of thing. It allows you to tell that something deep is going on in that material. And to really understand it, then you have to get into quantum physics and all of those things. And what the India detector does is exactly that. The US is measuring one polarization all the time. And just as you said, we need two detectors to be confident, because in the past, it wasn't like this multiple things per week. But we were incredibly neurotic about saying something wrong, because that had happened already in 1970. So to avoid that, we had enormous amount of checks that if any signal ever popped up, we wanted a crack team to come in and disprove it. So we were given this exercise of a fake signal once. Can you find a fake signal or something? And we could just tell that the entire group was not ready to detect something real. All that we had in our pocket was a bunch of reasons to disprove that this thing had happened. But as a result, the two detectors are meant to detect really the same thing. And so if something's polarized the other way, in the US, you wouldn't be able to know, what's the polarization. Because India is on the other side of this globe, by, geometry, it's measuring something different. Just by location, right away, you win. So if that's installed, all of a sudden you can see if Einstein's prediction that gravitational waves just have two polarizations, is it true or not? And is there a third polarization? That's the key thing.
And you think there is some reason to believe there might be?
Yeah.
So, okay, you're not joking then. This India detector can actually contribute to that understanding, either, verifying what he had to say about polarization of the gravitational waves or not.
Yeah.
And that will make amazing, headline again,
Amazing.
The LIGO in India has proved Einstein wrong. I think we can live off the headline for 10 years.
Then I can retire. That'll be my mountain, I think.
And where is that project? First, where is in India? So where are we building this? Has the construction started? When do we see it go live?
Yeah, it's in eastern Maharashtra. So it's maybe, by driving, it's like 12 hours east of Pune.
And you do that drive routinely?
Yeah. I have never been there, in fact.
Oh, you've never been there?
Because there's no good helipad or airport or something, and I just don't feel like... Right now it's just open land, so it hasn't been built yet.
I see, okay.
It's the tenders for the construction and so on were posted earlier this year. And we expect companies to now bid on those tenders and then start the construction early next year. And that would be, essentially leveling the land and putting these tubes there and building some buildings and so on.
And this is all funded by Indian government?
That's right, by Department of Atomic Energy and Department of Science and Technology.
Yeah, that is incredible. I mean, we have, I think of late I've become pretty interested in overall, funding and the research ecosystem in India. But these kind of initiatives at least are, are quite encouraging. And this is like as fundamental science as it gets. This is not trying to build something which will, this is, just helping us understand like deeper understanding of universe, as like really hardcore science objective. And it's good to see there's a investment, etc. I'm guessing, you probably have your own challenges with the project in terms of, speed and pace and all that. But in overall, as long as we get to see So what's the optimistic scenario here? Next 5-6 years we see it go live?
Yeah, that's right. I think optimistic scenario is 2030. And, and it's a big project, and there are a lot of moving parts. And even in US, I think we struggled a lot at the beginning because it's just, no one has expertise in this field. Even in the US, there were no gravitational wave scientists, you would say. There were a bunch of us who were just learning how to do it.
Yeah.
But most everybody came from some other field. I was like one of the first, you would say, like pure blood, like raised from a early age as a gravitational wave scientist. But now there's many people like that. So, I mean, surely something like that will happen. But the advantage for India is that it's been done twice at the basic level.
Yeah.
Of course, this is the third detector, so we're not just going to build the same thing as what's in the US. We have all these lessons learned. So this third one is going to be the, hottest, shiniest gravitational wave detector in the world. It will, we won't have to go through all these teething problems.
Yeah, quite incredible. Maybe, we have talked about this in the past, but maybe I did not appreciate the gravity of, this. This is, and what you're saying is going to be a really cutting edge, third installment of LIGO.
Yeah.
It has the potential to, deepen our understanding of fundamental physics. And it's probably most advanced kind of experimental science thing that's going to happen in India this decade or next. So the potential to like really
no, not just India.
Anywhere in the world.
This will be the highest precision measurement instrument that humanity has ever made, by far.
Yeah, I think you should do a roadshow or some kind of tour in India to talk more about this. More people should know about this. I think
I'm putting together a roadshow.
Yeah.
Yeah, because I found it scandalous. This is, when I first read about relativity, I was not even in university. I was working in as an auto mechanic, and I had just checked out this book on relativity from the library. And I looked through this thing, and it wasn't a feeling like, oh, that's kind of interesting. The feeling I got was, are you kidding me? Is it like either this guy is crazy or this is how reality is, but we're just not telling anyone. So it's somehow scandalous in one way or another.
Yeah.
And I went and I talked to my father about this. I said, did you know about this? And you didn't tell me about this? And he said, no, that's not right. There is an ether, and that's how things... And he was still believing in the ether theory in the 1990s. I thought it was scandalous. And so I thought this roadshow is important because everybody who is interested in technology and science in India should know that this amazing thing is happening. And you can take part of it. There's something there for everybody. If you're interested in difficult engineering or mathematics or fundamental physics or astronomy, any of those things, this is the thing. Everybody in the world is going to be waiting for this thing to come online because the scientific outputs of this will be front page news all over the place. And without India, there's no game.
And it will also encourage interest in science from early age. A lot of students will hear about it. They'll get to do their summer projects there, go to this place, look at how all this precision technology works, from like how what CERN has done for last 30-40 years. That's the only place I guess in the world for people to go to for particle physics exposure. And I think this is quite fortunate that somehow we're able to get funding for this, and looks like project has come a long way. You've been at it for what 7-8 years for the LIGO-India?
I've been trying to get it going since 2007.
2007. Okay, so one more 20-year project. So maybe you'll keep doing this 20-year projects. Maybe you will, by choice.
I didn't think it would take this long.
Yeah, most thing worthwhile taking. But look, if it comes online next 5-6 years, I think.
Yeah.
I am struggling to think of any other scientific endeavor in the country today on the fundamental sciences which has such incredible potential, and feel a little bad also that I didn't know much about it, but I think you should totally do a roadshow.
You should not feel bad. If you haven't heard about it, that's my fault.
Well, okay, let's shared responsibility, but we are making amends through this podcast.
That's right. But the opportunity is there. Like these days, like what are the buzzwords in science? It's quantum and AI. This is the thing which does that. I mean, it is so heavily involved in the design and construction of this thing, AI tools. And then finally, if you took away the idea of quantum entanglement, the number of signals that we find would just shrink. The universe would become quiet all of a sudden. But it's this use of spooky quantum entanglement that lets us actually hear what's happening in the universe. And there's just another one of those things that knocked me off of my feet. if you had told me that when I first started, I would say, you're just hallucinating.
Okay, I think I'll have to again switch back on your world's greatest science communicator button on, and let's retrace it. What is entanglement, and how does it fit in this conversation?
And we were using laser light to make these measurements, and most of my life is not about gravitational waves. It's about finding noise in the experiment. So it's a very, it's as a student, you're working and all of your friends are finding things and discovering things, and you're just sitting there in the dark in a basement looking at different kinds of noise.
Yeah,
it feels dispiriting, but it turns out to, that's all that's there in precision measurement. That's what you do to finally find that golden nugget you're looking for. But when you get down to it, finally, quantum mechanics gives you a limit. There's a precision limit to how well you can measure the world.
Yeah.
And you can think about it by saying, here we are, and we're under these bright lights. And the reason we're under these bright lights is so you can see things, and see what's you're illuminating things. But there's a limit. And if you increase the power of the lights by 1,000-fold or something, you're disturbing the measurement in some kind of sense. And so the more light you put on things, you disturb things.
Right.
The less light you put on there, the less you can see it. And so you don't want to overpower it, because you don't want to see things being disturbed. You're trying to observe them in their natural state, like the gravitational wave. And why is this happening? It happens because there's sort of a random nature to the way light particles hit our detectors. And so when we're listening to the universe, it's like when you've put on your Bose noise canceling headphones. There's a little bit of a hiss. You're always hearing this tss if you're in a quiet place. And that's just because the noise cancellation system has a sort of hiss to it. But it's the same when you're listening to the universe. Most of the time there's no signals coming in. And so you just hear a hiss. But that hiss is the individual arrival of photons hitting your detector. You're hearing quantum mechanics when you listen to the LIGO detector. And we said, well, I said anyway, I guess that's it. Here we are at this limit. If we raise the laser power, our optics and things will start to melt. So let's not do that. If we lower the laser power, the hiss will get louder. So we don't want that either. Luckily, Kip Thorne is a visionary, and he and his group had been working on the idea of how to evade the uncertainty of quantum mechanics even since the 1970s. I had heard about it, but I thought, it's academics, they like to work on things. Probably it doesn't impact my life. Entanglement, it seems like esoteric quantum mathematics or something. What's it got to do with me? But it has to do with everything now. And entanglement is the idea that sometimes things in the universe are not really two things. They're just one thing. So I'm explaining this in my way. And depending on your quantum mechanics religion, you'll explain things in different ways. So you had these many worlds people on your podcast before. I'm just not part of that. Right? I don't believe any of that's true. The way I think about entanglement is, what is a photon actually? There is no photon until you've measured it. What it really means is that you've made a fluctuation in the electromagnetic field, like a laser or lights or something like that. And rather than be a wave that just goes in one direction, it's actually a wave that emanates from a single place and goes in two directions. And if it's like in a pond, if you're sitting there in two places, if you're taking a bath, maybe this is a good example. Your toes are out of the water and your head is out of the water. Somebody drops a rubber duck in the middle, you'll get a wave at your toes and at your head. It's not really two separate things. It's one circular wave that went and you felt it in two places. So it feels like it's been two, I don't know what you would call that, duck-ons or something like that, but two wave-ons or something. It feels like two things that are entangled. But the way I look at things is entanglement just tells you that there's something that appears to be two things, which is actually one thing. So getting back to your question, there is this hiss. What we do is say, indeed, the universe is noisy and quantum mechanics leads to some sort of precision limits, but you can sort of cheat a little bit here and you can sweep the noise under the rug. And the way you do it is make sure that when the random photons come to your detector, they're really each two are one. So they come in pairs. And so the noise comes in these bursts. That's like So when the noise comes on, it's a lot louder than normally would be. But when it's off, it's much quieter. So we just listen for the music when the noise is low. And then you piece together what's really going on. So if you're talking to somebody and there's, a train coming by periodically, as long as the trains come and go quickly, you can still piece together the conversation better.
Got it.
So that's
Okay.
essentially what it is.
Got it. So, okay. So while we are trying to measure things related to this massive gravitational event around the universe, literally in this case, but a lot of precision engineering at the at a quantum level is what's enabling for us to be able to detect something so faint and remove all this noise, etc., and so on. Just so Rana, I know you also generally take very active interest in sciences in India. Just one is obviously LIGO is kind of, maybe I'm guessing, key motivation to be involved, but I think you do visit here often, collaborate with various people. Just talk about your relationship with Indian sciences.
I'm born in the U.S., right? So what's India got to do with me is a normal question. But I've been, I visit here periodically as my family would come here and
were you called ABCD growing up?
I never heard that phrase until late. I went to TIFR and someone called me that.
Right.
And I said, there's no C for me. There's nothing to be confused about.
Right.
I'm not.
You were born enlightened.
Yeah, I was just, the Indianness was just sort of baked into our family life. It's more like it was just, but we lived in a community where everybody was of some different stripe. And so didn't feel like, if you're in a zoo, everyone's their own kind of animal. It doesn't feel anything strange about it.
Yeah, right.
But I think my interest came because, I grew up mostly in the state of Florida, which is, at the time, was, of all the states in the U.S., was second to the bottom in education. And so I could see that a lot of people are struggling with things that I wasn't struggling with. And, what's that all about? My parents are Bengali. I'm Bengali. And so this thing about doing mathematics as a child and playing chess all the time was just baked into the culture. But my father was an engineer. And so, and the culture back at that time was not, it was considered embarrassing if you couldn't repair everything in your home. And I don't know how they did it because they didn't come from that kind of background. But every weekend morning, we were out there in the garage doing something, fixing some, dangerous stuff. If I had a child, I wouldn't do that. But electrical wiring, automobiles, that kind of stuff. So I've been trained as an experimental physicist since age 3, I think.
Yeah.
But I could just tell there was some, that's just not going on in the local community. People are not getting this intense science and engineering training at home.
Yeah.
And so there's just a big level mismatch if you come from that. And then in 2007, I made my first scientific visit to India, and I went to a conference, and I was starting to see, what is the level of people, and I was also kind of a junior scientist in the U.S. at the time, but I was starting to see what are the differences in capabilities and opportunities mainly, and it's mainly opportunities, and I would see, I'm not special biologically or something like that, but I happened to be grown in an environment that it was just super easy.
Yeah.
I was not even a good student. I'm just really I'm not being modest here. It is unexceptional. But
good to know. One thing you're at least claiming to be not good at. Yeah. That's reassuring.
You don't need to be, I think. I didn't have much of an interest in science or any of these things at age 10 or something. It was just a thing that was just normal, I would say. But I could see in India there were people that were much more talented than me and a sort of raw intellect, but they just didn't have this opportunity. It wasn't, I grew up in a NASA town near the Kennedy Space Center. So if you can imagine this thing, everyone who I go to school with, their parents are NASA engineers or scientists or something like that. So the level of what is expected from you is so much higher because all of your peers, everyone's taking calculus at an early age, and that's, but you're not considered special for that. That's just a sort of average level. And this idea of getting involved in science, I thought, I don't want to do this NASA stuff. My parents, my uncles, everyone's doing this NASA thing. I'm going to do something else. Keep me out of space. But that, it's that kind of opportunity that you can just go, everyone is a engineer or a scientist. If you want to get into that kind of thing, the world is your oyster if you grew up in a community like that.
Yeah.
But that's not the case everywhere in India. There are some places like that. But I thought, wow, what a untapped resource. You have this tap, which with gold, and if you just slightly crank it open, you're winning.
Yeah, I really hope that tap gets opened in a much bigger way in the coming years. And I know you are doing your bit, I think, and I think this LIGO-India can end up being a huge catalyst for really driving genuine cutting edge experimental research in India, like many other efforts are going on. Just speaking of environment ecosystem, I want to maybe a two-part question. You've been at Caltech for a while. Caltech is this famed American institute. Einstein visited a long time back. So many fundamental discoveries in 60s, 70s, 80s, and all the way up to gravitational waves. Recently, Richard Feynman is world famous, I guess. Second character after Einstein, who is pretty well known. I know at Caltech. Just talk to our audience about Caltech. What's unique and different about Caltech. Why it has continued to make such phenomenal contribution over 100+ years.
Yeah, I mean, at all institutes, there's this sort of feeling like, this is the place where we have the secret sauce.
Yeah.
And I went to grad school at MIT, and I always had this kind of, I know that people in California are kind of lightweights. Like here at MIT is the, where the real hardcore science is going on, and we're the serious people. And so it's a different feeling at each of these places where you go. But, over the years, I visited other campuses here and there. And for the first day, I would say, wow, what a beautiful campus. Maybe I'll move here. Maybe I'll leave Caltech and come here. But after a day or two, I just think, nah, it's not going to happen. And the reason for it is since day one, when I was still hunting in the noise and there was no signals and the whole world was very skeptical about this project, the other people on the physics faculty at Caltech would come to my office with some sort of pretext. And then right before leaving, they would say, I don't care what anyone says about you. I believe in you and what you're doing. Just let me know if you need anything. I can support what you're doing. And that's been a kind of thread the whole time I'm there. I can just wander around kind of a small campus, but people from other departments have nothing to do with what I'm doing. And they would say, oh, aren't you the guy who's working on that thing or this thing? And they let's have a chat about what you're doing. And the whole atmosphere on that campus is this kind of, it is that kind of feeling like we're special and we can do these things. But the real special thing is in this supportive thing, that if you really want to do something and your colleagues say, I don't understand why he wants to do this thing, but he seems to be really into it.
Yeah.
Let's figure out a way to make it happen. Like I said, I want to shoot my quantum laser across campus underneath through the tunnels, and I want to connect it to this other person's lab and then bring it back. And I talked to the Caltech president, and he said, sounds like a cool idea. Let's do it. And that was the entire approval process. And if you're at a normal university and you try that, that would be just paperwork and safety and all kinds of things that would go on.
So you're saying the environment says that you can be genuinely crazy and have these moonshot ideas, and it's very receptive and open, encouraging of making it happen, as opposed to finding
because of belief. That there's been this track record of that working out. And it doesn't matter if you try 10 things and 9 things fail. So what? You learn something great from it.
And part of my motivation asking the question, Rana, was how do we get Caltech of India? What does it take? It's at some point, as is 17% of world population, as you mentioned, there is a enormous amount of intellectual talent, but you need also that environment and the ecosystem. So what will it take for us to eventually end up in Caltech or MIT or whatever else, world-class institute here?
I mean, MIT, I won't speak to, but
right, you've shifted, allegiance
I've
completely.
Shifted allegiance.
There's a lot of religion in science, which slowly, but
I think it can be done, but it's, Caltech is not really just about this play. Like the place is sort of irrelevant. You have to have that mood. The belief by everybody in there that, this is the place where this can happen, and it's that belief that, look at this thing. Like here's these last 20 things. We have these stories where this was really difficult and this person did it. It was really challenging, but because of whatever, like random encounters, Richard Feynman showed up or something like that. you can actually do these things. And if you fail, it's not a big deal.
Yeah.
And I was told there by one of the senior faculty, Jeff Kimball, when I first got there. And he said, because I came to him and I said, look, I'm a junior guy and I really don't want to fail in my first thing. I really want to do it. And he said, look, if you're Caltech material, you should always be afraid of failing. You should always be on the edge of failing, that you're about to embarrass yourself or something like that, because otherwise it's not interesting enough. If you're doing things where you think that's 50-50 is going to work out, you should probably head down the road to some second-class place. And I keep that, whenever I'm worried about failing, I keep that in my mind.
And that,
it's like I'm an experimentalist, so I care about outcomes at the end of the day. And I think the truth is that, what's your return on investment in terms of scientific advancement? And it doesn't matter if you fail 20 times even. You just got to get that one awesome thing. But if you just make sure you're going to win all the time, you're just going to be in the incremental game, getting another digit on some constant of nature or something like that. But you won't make a discovery. Like, you wouldn't want to go to cocktail parties and talk about, I added another digit to the mass of the proton or something. You want to say, this is one thing, here's how you all thought the world works. It's not true. Because I and my team, we spent all these years struggling for it. We've now revealed a new thing about the real nature of reality in the universe. And or we've discovered a thing that's going to help millions of people or something. I think in India you can do that, but there's more skepticism here. I think people you bring up an idea and immediately people have a lot of reasons why it's not going to work, which is also valuable. You don't want to just be foolishly optimistic. You should be ruthlessly, concrete about all the reasons why it's not going to work out, and then go attack those things. And that's the LIGO experience. I would say at the beginning we started and the sensitivity was, I think it was 10 million times worse than the design. Have you ever made anything like, it's like if you bought an automobile and instead of 100 kilometers per hour, you could go at something like 1 millimeter per hour and then declare success or something like that. But there was that spirit that every time we find a limit, we're going to break that limit. And then we'll find 5 more limits and we'll break those limits and we just keep on going. And in the end, it's going to work out for us. And if you build a community of people who believe that, maybe 90% of us are going to fail, but the point is the collective here will succeed in a big way. And then encourage everybody. And you've seen this with students, I think, that if you get them into a place where they're positive and they feel like they can succeed, what they'll accomplish, even if they fail, will be much greater than if they don't have that belief.
I think made me introspective. I think this is, what you're saying is a good food for thought for anyone in a leadership position in any organization, whether science or outside. How comfortable you are with people being on the edge of failing most of the time, as opposed to coasting along on something which is well-known chance of failure, and you can almost model your risk and factor that into everything and so on, versus like this is unquantified risk, get off by a factor of billion and still have a second and third shot at doing something, which is how breakthrough happen. I guess unavoidable. You can play it safe for next 100 years and nothing is going to come out of that unless people are willing to operate on this boundary of almost failure or repeated failure until something works.
And I think people need to go out and tell their stories about their failures more often. So that you can just see it's a regular thing that happens.
Part of building this whole, research ecosystem, environment, and mood, as you call it, it's and I'm guessing your answer is probably going to be all of the above, but still, there is people get inspired about science in their, middle school, high school years. If they go to a good environment for their education, that's when in some ways they kind of make a choice whether to pursue career research or not, who their mentors are, the kind of projects, exposure, that plays a role. Making a choice to pursue a PhD, which is there when you really make a transition to be a serious researcher or not. Funding sources, both government, private, and so on. I'm asking this question, someone who's very deeply interested in, at least being helpful to the research ecosystem in India. I think there are many other people like me. Where do we start, And if you can't say all of the above, to focus your energy, what's a good way to at least some way, catalyze
No.
the ecosystem a bit more than what's being done already?
I always have one answer for all of these things, is just exactly how we do things in science. Is you build a quantitative model of your system, and then you look at all the things and ask, like I always ask myself, where is the place where I myself can have, like, given what resources I have, I can make the maximum impact. So I'm not going to go work off, like in something like history or neurology or something, because my personal skill set doesn't do anything for those people. I can be just a bit player on the side. I think there's several levels. I mean, of course, in India, there's the financial resources an issue, but I mean, that maybe now is less of a problem than it was 40 years ago. I think a lot of it is this kind of thing. There's a feeling that, what is world class and what can we accomplish in India? Like there's that sort of belief gap.
Yeah.
And I think you have to analyze and be realistic about it. But there's many areas in which the talent is there and the resources are there to make a real world class impact. But there's a belief problem there that, oh no, it's just India, can we do it or something? But you can do it. If you give me just 10 top tier kids from any of these high schools or universities. I went to this Ashoka Lodha Genius program last year, and there were all these kids who were teenagers, like 13, 14, and 15. I was just blown away. I've never seen anything like that in my life.
Yeah.
That kind of talent in under 18. And I'm not exaggerating at all. Like if you give me 5 of those for 5 years, I'm sure I can make some huge, like, front page news discovery.
Oh, wow.
You don't need anything more than that. Yes, I mean, if you have the talent, the funding will come for someone who's really going to do something like that. But I would say it's not a fault, but it's the job of mentors now. When you get to be at this middle-age level, you have to say, now let me zoom out of myself, get away from my own ego, and say, imagine myself as a piece on the chessboard, and what's the right moves for that piece? Probably it's not, at age 50, you're not going to be the one working 22 hours a day in the laboratory 7 days a week. That's a kind of intensity that you get when you're doing your PhD or something like that. Now your role is to empower those people, like was done for me by Kip Thorne and Ray Weiss. They took me at whatever nascent stage I was and then amplified me in a way so that it could make me powerful. And that they knew that at that time. They were still doing their own work, of course, but they put a huge amount of effort into making sure that we were growing. Because you'd say, if I have one egg, I have one egg. But if I have a chicken, I've got a lot of eggs. And then, as you said, a place to hold the chickens is even better.
Yeah.
So you have to be realistic about that. And that's the job of mentors now, I think, in the science and technology world, is to say, I want to amplify my effect by 10x or 20x or 100x. And what am I going to do for that?
Yeah, last year, on LinkedIn, just on a whim, I just posted a very small note with the title, "Where are India's Nobel Prizes?" And it got a huge traction. I was surprised that, among all the posts I've ever done, this got the highest number of reposts forward. So there is, this like simmering, unrest and desire, because in some ways, India has done very well on many accounts. We are, finally very well noticed, probably too noticed now with everything Trump is doing on the world stage. But simultaneously, there is recognition that, we're punching well below our weight. And there was a time 100 years ago when we were punching way above our weight. It was one of the poorest, deeply exploited country. Yet, C.V. Raman right here, and Chandrasekhar, Subramaniam, and S.N. Bose, who should have probably gotten multiple Nobel Prizes, if not one, right? And so on.
Meghnad Saha.
Exactly. And now, it's we don't have many contenders, and it's been a while in science, what will change? As you say, like, there is so much, young talent, and you say in 5 years they can do, with the right kind of mentorship, how, okay, what's the right way to ask this question? Will we see Indian Nobel Prize in next 20 years?
Sure.
Yes?
Yeah. Why not?
No, we should see. That is the easy answer. Will we see?
I think if people who want to see this say, I'm going to commit myself to making sure that we make 5 Nobel Prizes in 20 years.
Yeah.
That's a thing that you can do. That's not science fiction. That's not me kind of blowing hot air or anything like that. It's just you have to have the willpower and then be focused. And if it's the whole, this is the whole meaning of entanglement, quantum entanglement, is that if you can take a bunch of individual photons and you can make them all aligned and coherent, the power of that is immense. And it goes like the difference is like the square root of n.
Yeah.
And so in the US, whatever, maybe you have 10 million people who might be, you could harvest for something like that of the population, but they're not coherently working, right? It's not a Manhattan Project kind of thing where everyone's on one thing.
Yeah.
In India, if you say, in the intellectual technological space, what's the N that I have? It's vast.
Yeah.
Maybe it's not the whole billion population, but could be 5% of that or something. And if you can amplify their contributions by square root of that factor, now you're saying if Indian science has a 1% chance of a Nobel Prize per year, but now you get people working in a coherent fashion, like you would do in quantum computing or something, you make it all entangled, then the factor you get is 1,000x just on that number.
Yeah.
And so now it's more like several, Nobels per year. So, probably we can't make the entire country of India work in a coherent fashion, but you have to up that coherence factor and minimize the decoherence and say, what are our moonshots that we're going to do as a country? And here are some areas where, sure, there's competing efforts in other parts of the world, but the advantage that we have is that we can mobilize people in a coherent way with, relatively, it may be a lot of effort, but not a lot of resources. And you have to get people to believe that this is a worthwhile thing to do, and then we just do it.
Yeah, I think that's a good puzzle for at least all the people who are interested in Indian science to kind of ponder over and see how do we align all this effort and in a coherent manner to be able to enable that. Even a few Nobel Prize, I think, will catalyze a whole ecosystem, because Nobel Prize, brings in some ways a lot of attention to whatever is being done. It inspires a lot of younger people. They want to get into science and so on. A place like Caltech, I'm guessing, gets at least one every decade, if not more. Country like India should definitely aspire to outcompete, Caltech eventually.
India should have 5 Caltechs, I think, and spread about in the country. And it's good to have a couple in the big cities. And I think a good model is to also have some out in a rural area.
Yeah.
So then you can catalyze build a whole tech community around it that's kind of supporting this and sort of bilateral exchange. And each of them can be devoted to a few different, like centers of excellence or something. That's all you need, I think. All the Nobel Prize winners that have hired me or I've worked with in the past, there's a common thing with them is that they're really unusual when you get to know them. They're, personally.
Yeah.
What's really going on underneath the hood?
Yeah.
How did that person get a Nobel Prize or this other person?
Yeah.
They didn't. If you look back, like early in their days, you would not have predicted that this is someone who would have gotten it in a lot of cases.
And they're all unusual in their own way?
Yeah. They're unusual in their own way. And I would say that maybe the common thing that they have is they understand this multiplier effect. And if you look at Kip Thorne, for example, people know him for his, great discoveries and ideas about black holes, but he's not a one-man show. What he does is he predicts things that are like, this looks promising, and let me get some really sharp people together and get them interested in this area, and then they're kind of self-motivated. The whole idea about using quantum entanglement to do something came from one of his students, Carl Caves, who sat around, and for a decade, I would say in the 70s, Vladimir Brzezinski was coming from Russia, from Moscow. Stephen Hawking was a regular visitor. And they would sit around and talk about these fundamental things. What's the universe like? Fluctuation, something. And it gave birth to these things. But Kip has a vast array of students who work with them.
Yeah.
And he's the one kind of introducing them to the interesting problems. But he knows how to kind of nurture that thing. And it's because he's an extremely generous mentor. Whenever he and I interact, he's extremely generous about giving me credit and encouraging. And he builds you up in a way that after a Kip interaction, it's like a scattering event. But everyone comes out of it feeling like they're very smart.
Right.
And that's a remarkable thing. You talk to Kip Thorne and you feel smart instead of dumb.
Right.
Whereas there are some Nobel Prize winners, if you talk to them, you don't feel smart afterwards.
Got it. So yeah, what you're saying is science is also, it's a collective enterprise. It's not a lone genius kind of thing. You have to build upon other people's idea.
Yeah.
Help grow other people around you, and collectively. Because
Yeah.
science is also getting harder and harder. It's no longer patent clerk in Swiss office can in the
I don't think
evening
so.
fiddling figure it solves universe's problem.
I have to say it's like my main growth in the last 20 years or something is like learning how to be a better mentor. I'd say the main thing.
Yeah.
I'm not there yet, but that's, I think, super important if you're a scientist and maybe there are some areas where it's just a few people are working, but for some of these large experiments, you're running like 20 people or 30 people or something like that. It's not a large corporation, but it's still, if you want to get the most out of 20 or 30 people, that's a different coherence problem than if it's 2 or 3 people.
Right.
2 or 3, you can all be independent and have a vision or something, but if it's 20 or 30 people, you have to grow those people. They have to be feeling like they're invested, they're getting rewarded. It's like a whole different sort of problem.
Just on the closing note, Rana, what's exciting in science today? Feel like the next 10, 15 years, other than the LIGO in India and more cooler stuff, that we learn through gravitational waves. What are other things, which you are personally interested in, paying attention to?
Yeah, I think I'll just talk about physics. I think that's where maybe I'm most credible. I would say, of course, there's a lot of hype around quantum computing and what's it all about.
Yeah.
I'm not working directly in quantum computing, but this idea of what can we do by using the technology which goes behind quantum computing, what's that good for? And I think about this for the LIGO in India, but then just generally, what would we like to do? Like, what was Stephen Hawking working on in 1974? It was essentially the problem of quantum gravity and what is going on with space and time at the edge of the event horizon. How are we going to get to something like that? We can, keep on theorizing the rest of our lives, but we want to find out, like, what's some real evidence, like a real detective clue that leads us down that trail. And I think that's in this thing of harnessing extreme coherence and entanglement for quantum measurement.
Yeah.
And there's huge payoffs to that just on the practical side, but my main interest is a fundamental physics. So I think it's possible using modern tools of AI to model that entanglement. So you can use classical machines to simulate quantum machines, and then use quantum machines to build better quantum machines. And using that kind of feedback, eventually we should be able to do measurements that allow us to see all the way back to the Big Bang, like not to t equals to 0, but t is equal to 10 to the minus 12 seconds. So that's my hope. I want to get a baby picture of the Big Bang when it's just been born but hasn't made its first squeals or something like that.
And you can see sequence of events which may enable us to be able to see that baby picture in our lifetime.
Yeah.
That's probably going to be worth of.
I mean, it depends on how long I live exactly, but yeah, I think so.
Yeah, things are accelerating. And we didn't talk much about AI today, but I'm assuming that also has probably some role to play, at least as an extremely powerful tool.
You had this fellow Anil on your podcast recently.
Yeah.
He wrote this great article about my recent paper about this, and what we're basically saying, there's a lot of change left on the table. Like, we've been doing a lot of optimizations using our brains that could be done by computers, and so like in the last few years I've been much more into this AI space just for experiments,
right?
And what can you get out of it? And as it turns out, there's maybe unsurprisingly, the things that I designed in 2010 using my wet brain are not as good as what machines can do.
Yeah.
So you may look in the future and ask, what is LIGO-India going to be doing? It'll probably not be designed by people, the next one.
Yeah.
All the things in the world are now designed by people, but in the next one, you may just ask that to build the experiment for you. And then what can we do? I mean, then it might be this kind of thing where we're really exploring the Big Bang.
Yeah, and that also is a probably good area for Indian scientists to pay attention to, because AI is possibly going to change how science is done, and every time there is a paradigm shift, then there's an opportunity to do things differently, and that's where probably given the vast intellectual talent that the country has to really embrace the so-called AI for science acceleration could be one enabler for
it is
right.
I mean, it's even AI for AI. I would say if we're using AI to, I hesitate to say AI. I feel like we're using these vast optimization tools. There's more that we can do to it. We can use that to design better ways, instead of circular feedback like this. And the great thing about it is, what's the step? If you're a high school student right now and you think this is something you want to do, this gets you like right up to almost to the top tier of the playing field immediately.
Yeah.
If you have access to a computer or something, you're right there. You don't have to, like what I do, you don't have to spend 20 years reading C++ or something like that to get into it.
Yeah, it's definitely exciting time. Rana, I want to, thank you for taking time to talk to me on this podcast. But your enormous contribution to science, I think your work, is up there. A lot of seminal contributions. I was looking at your H index, which is just off the charts. Maybe but more importantly, I think you're probably mentoring so many young scientists both in California but as well as in India. I think this LIGO-India project is extremely promising. I hope it comes alive in next 5-6 years, and I also hope a lot more people come up to support that. I think there is obviously government is doing their role, but both academia and the private sector can also pitch in, and I think it will be a huge boost to overall research science ecosystem in India. So thanks so much for everything you're doing for Indian sciences, and great to talk to you.
It was great to be here. This is a fun adventure. I just have to say, this is not like tough work for me. It's just so much fun to be coming back and forth and getting to play with science with all of these people.
Yeah,
so
and that's something makes me feel jealous. I think scientists have so much fun. It's the coolest job in the world. That's probably one reason for kids to consider science as a career.
Yeah, this is my advertisement. It's a lot of
shoot
fun.
lasers at the basement, and your institute president is cool with that. What more can?
The amount of stuff that I've destroyed with my lasers is dramatic. I don't want to talk about it publicly.
It's good for you, and have your lasers. Yeah, thank you. At SparX, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to SparX on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.